Welcome to Module 3 of Environmental Engineering, Part 2. Today we look at the shapes of sewers and why each shape exists. The shape of a sewer is never accidental. It is chosen so that the sewer carries its designed discharge efficiently, stays self-cleansing at low flow, and resists external loads safely. Six factors guide the choice: hydraulic efficiency, the variation in discharge, structural strength, the method of construction, the subsoil and site conditions, and finally cost and material. Each shape we study makes a different trade off among these six. The first and most common shape is the circle. Hydraulically, a circle is the most efficient section at full flow. It gives the smallest perimeter for a given area. Structurally, it has no corners, so stress is distributed uniformly, making it the strongest section. It is also the cheapest to manufacture as precast pipe. Its drawback shows up at very low flow. Below about 1/4 of its diameter, the velocity drops sharply and the sewer begins to silt. So the circle is best for sanitary and combined flow that runs nearly full. To solve that low flow problem, engineers developed the egg-shaped or ovoid sewer. The narrow invert at the bottom keeps even small dry weather flows at a high depth, so the velocity stays self-cleansing. The wider crown above handles peak storm flow. The proportions are usually 2:3, width to height. Egg-shaped sewers are costlier and structurally weaker than circles, and they are not made as precast pipe. They are built cast in situ in brick or reinforced concrete. The famous example is Sir Joseph Bazalgette's 19th century London sewerage system. Next, the rectangular sewer, essentially a box culvert. It is simple to design and simple to construct. It can handle very large discharges that no single round pipe could carry. Hydraulically, however, it is less efficient than a circle of the same area, and its flat invert leads to poor self-cleansing at low flow. Rectangular sewers are therefore used mainly as storm water drains in city streets and as box culverts crossing roads and railways. For very large trunk and outfall sewers, the horseshoe section is the classic choice. Its arched crown carries vertical earth load extremely well. The wider invert gives more carrying capacity than a circle of equal height. Horseshoe sewers are constructed by tunneling, lined with brick or reinforced concrete segments, useful where great depth makes open-cut excavation impractical. You will find them in the intercepting sewers of Mumbai and Kolkata, and in modern equivalents like London's Thames Tideway Interceptor. Two smaller scale shapes now, parabolic and U-shape. The parabolic sewer is used for small discharges in shallow installations. It is easier to construct in difficult subsoil where deep excavation is restricted. The U-shaped sewer has vertical sides and a semicircular invert. It is particularly easy to cut into hard rock where the sides can be left vertical. Both are commonly seen in hilly or rocky terrain, in industrial effluent drains, and in small village drainage. Two more specialized sections. The semi-elliptical sewer has its long axis horizontal, a wide flatter section used for very large discharges in soft soil where excavation depth is limited. It is structurally weaker than the horseshoe because of the broader span. The basket handle sewer is a close cousin of the egg shape, a wide arch top with a narrow rounded invert. It maintains self-cleansing velocity at low flow and carries large storm flow above. Both appear in old combined sewerage systems of European cities. Let us compare them side by side. The circle is best for small to medium sanitary and storm flow. Excellent strength but poor self-cleansing at low flow. The egg shape is best for combined sewers with large flow variation, excellent self-cleansing, only moderate strength. The rectangle suits large storm drains. The horseshoe wins for deep trunk sewers and tunnels. Parabolic and U shapes are for small, shallow, or rocky installations. Semi-elliptical handles large discharge in soft soil. Basket handle is for varying flow. For your GATE, ESE, and university exams, three associations are worth memorizing. For self-cleansing at low flow, the egg-shaped ovoid sewer. For hydraulic efficiency at full flow, the circular section. For structural strength against external load, circular for buried pipes, horseshoe for tunnels, The selection criteria to remember are quantity and variation of discharge, velocity at minimum, average and peak flow, external load and subsoil, and finally method of construction and cost. The rule is simple: match the shape to the flow, steady full flow, choose circular; highly variable flow, choose egg-shaped; very large discharge in tunnels, choose horseshoe. That is Module 3. See you in the next lesson.